Welcome. In this video, we will explore a fundamental application of differential calculus, rates of change. By the end of this session, you will be able to use derivatives to model and solve problems involving how one quantity changes in relation to another. Let's begin with a classic problem to illustrate this idea. Imagine a 5-meter ladder resting against a vertical wall. Its feet are on horizontal ground. We can model this with a right-angled triangle. Let's say the ladder starts to slip. As it slips, the distance x from the wall to the base of the ladder increases. What happens to the height y of the ladder on the wall? As x increases, the ladder slides down, so the height y must decrease. This shows that the change in one variable, x, causes a change in another, y. This relationship between changing quantities is the core of what we call a rate of change. It describes how one variable's value changes in response to another's. In this scene, we will formalize the concept of a rate of change and connect it to the derivative. Our objective is to understand that the derivative da represents the instantaneous rate of change of y with respect to x. We've seen that if we have a function y equals f of x, its derivative f prime of x, or diet, gives the gradient of the tangent to the curve at any point. This gradient is not just a geometric property. It has a powerful physical interpretation. It tells us the rate at which the function's output, y, is changing for a small change in its input, x. Think of it this way. If you have a graph of distance versus time, the gradient of the tangent at any point is the instantaneous speed. It's the rate of change of distance with respect to time. So, the derivative dx is the instantaneous rate of change of y with respect to x. It measures how quickly y is changing at a specific moment or point. This concept is fundamental to modeling real-world phenomena. For example, dH/dt could be the rate of ascent of a person on a Ferris wheel, measured in meters per second, or dc/dt could be the rate of change of a person's lung capacity in liters per second. In summary, the derivative dx is the mathematical tool we use to quantify how one variable changes in relation to another at any given instant. Let's apply this concept to a worked example. In this scene, we will analyze a function representing a child's ability to understand spatial concepts. Our goal is to find the rate of improvement at different ages and interpret the significance of the first and second derivatives. The ability, a, is given by the function a equals 1/3 times the square root of t, where t is the age in years, from 5 to 18. First, let's find the rate of improvement, which is the derivative dt. We can rewrite a as 1/3 t to the power of 1/2. Using the power rule, we differentiate to get dt equals 1/6 t to the power of -1/2, which simplifies to 1/6 times the square root of t. Now let's find the rate of improvement when a child is 9 years old. We substitute t equals 9 into our derivative. ddt equals 1/6 times the square root of 9, which is 1/18. This means that at age 9, the child's ability is improving at a rate of 118 units per year. What about when the child is 16 years old? Substituting t equals 16, we get dt equals 1/6 times the square root of 16, which is 1/24. The rate of improvement is now 124 units per year. Notice that 124 is smaller than 118. This suggests the rate of improvement is slowing down. Let's confirm this with the second derivative. We differentiate dt again. Rewriting it as 1/6 t to the -1/2, we get d squared a over dt squared equals -1/12 t to the -3/2, or -1/12 times the square root of t. For any age t between 5 and 18, t is positive. Therefore, the square root of t is positive, and the entire denominator is positive. This means the second derivative, d squared a over dt squared, is always negative. A negative second derivative tells us that the rate of change is decreasing. In this context, it means that while the child's ability to understand spatial concepts is increasing, the rate at which it increases is slowing down as they get older. So, we have successfully used the first derivative to find the rate of change, and the second derivative to describe how that rate is changing. Now, let's look at another common application. Marginal cost in economics. In this scene, we'll define marginal cost and see how it's calculated using derivatives. Our objective is to understand that the derivative of a cost function, c prime of x, gives the marginal cost, which is an estimate of the cost to produce one additional item. Consider a factory where the total cost in dollars of producing x items each day is given by the function c of x equals 9500 plus 12x plus 8x to the power of 0.8. In economics, the marginal cost is the cost of producing one more item. We can estimate this using the derivative of the cost function. The marginal cost function, c prime of x, is the derivative of c of x. Differentiating term by term, we get c prime of x equals 12 plus 6.4x to the power of negative 0.2. Let's find the marginal cost when 150 items are produced. We substitute x equals 150 into the marginal cost function. C prime of 150 is approximately $14.35. This value represents the rate at which the total cost is increasing when 150 items are being produced. A key interpretation of marginal cost is that it provides a good estimate for the cost of producing the next item. In this case, it estimates the cost of making the 151st item. Let's verify this by calculating the actual cost of the 151st item. The actual cost is the difference between the total cost of 151 items and the total cost of 150 items. This calculation gives us approximately $14.35. As you can see, the marginal cost, which is the derivative, provides an excellent approximation of the actual cost of the next item. This is a powerful tool for businesses to make production decisions. In this scene, we will tackle a more complex problem involving related rates. This is a common topic in IBAAHL. Our objective is to use the chain rule to find the rate of change of one variable with respect to another when both are related to a third variable. Consider a compass. The arm with the needle is 8 centimeters long, and the arm with the pencil is 9 centimeters. The angle between them is theta, and the radius of the circle it draws is r. First, we need to find a relationship between r and theta. We can use the cosine rule. The cosine rule states that r squared equals 8 squared plus 9 squared minus 2 times 8 times 9 times the cosine of theta. This simplifies to r squared equals 145 minus 144 cosine theta. Now, we want to find the rate of change of the radius with respect to the angle, dar/shate. We can differentiate our equation with respect to theta. Differentiating both sides, we get 2r times drdit equals 144 sine theta. Remember, the derivative of cosine theta is negative sine theta. Now we can solve for d/d. Rearranging the equation, we find that dar/dt equals 72 sine theta divided by r. This is our formula for the rate of change. The problem asks for this rate when theta is 60 degrees. A crucial point for calculus is that angles must be in radians. So 60 degrees is pi over 3 radians. First, we need to find the value of r when theta is pi over 3. Using our cosine rule, r squared equals 145 minus 144 times the cosine of pi over 3, which is 1/2. This gives r squared equals 73, so r is the square root of 73. Now we can find drdit. Substituting our values, drdit equals 72 times the sine of pi over 3, which is root 3 over 2, all divided by the square root of 73. This simplifies to 36 root 3 divided by root 73, which is approximately 7.30 centimeters per radian. This means that when the angle is 60 degrees, the radius is increasing at a rate of about 7.30 centimeters for every radian the angle increases. This example demonstrates the power of related rates in solving geometric problems. Let's work through another related rates problem, this time involving a triangle. Our objective is to find the rate of change of the area of a triangle with respect to an angle, using the chain rule. We have a triangle PQR with sides PQ equals 6 centimeters and PR equals 7 centimeters. The angle between them is theta. First, we need a formula for the area of the triangle, A, in terms of theta. The area of a triangle is given by 1/2 of B sine AC. In our case, A equals 1/2 times 6 times 7 times the sine of theta, which simplifies to 21 sine theta. We want to find the rate of change of the area with respect to theta, which is dA. We differentiate the area function with respect to theta. The derivative of sine theta is cosine theta, so dA dt equals 21 cosine theta. The problem asks for this rate when theta is 45 degrees. Again, we must convert to radians. 45 degrees is pi over 4 radians. We substitute theta equals pi over 4 into our derivative. d dt equals 21 times the cosine of pi over 4, which is root 2 over 2. This gives us 21 root 2 over 2. The units for this rate of change are square centimeters per radian. This means that when the angle is 45 degrees, the area of the triangle is changing at a rate of 1 root 2 over 2 square centimeters for every radian the angle changes. Let's work through one final related rates problem, this time involving a pantograph mechanism. Our objective is to find the rate of change of the length of a diagonal of a rhombus with respect to its angle. We have a rhombus with side length 20 centimeters. The angle where the arms meet is theta, and we want to find the rate of change of the length of the diagonal L. First, we need a formula for L in terms of theta. We can use the cosine rule on one of the two triangles that form the rhombus. Applying the cosine rule, L squared equals 20 squared plus 20 squared minus 2 times 20 times 20 times the cosine of theta. This simplifies to L squared equals 800 minus 800 cosine theta. We want to find the rate of change of L with respect to theta dl side theta. We differentiate our equation with respect to theta. Differentiating both sides, we get 2L times dl slash dθ equals 800 sine theta. Remember, the derivative of negative cosine theta is positive sine theta. Now we can solve for dl dθ. Rearranging the equation, we find that dl lash at dθ equals 400 sine theta divided by L. This is our formula for the rate of change. The problem asks for this rate when theta is 120 degrees, which is 2 pi over 3 radians. First, we find L when theta is 2 pi over 3. L squared equals 800 minus 800 times the cosine of 2 pi over 3, which is negative 1/2. This gives L squared equals 1200, so L is the square root of 1200, or 20 root 3. Now we can find dθ. Substituting our values, dθ equals 400 times the sine of 2 pi over 3, which is root 3 over 2, all divided by 20 root 3. This simplifies to 10 centimeters per radian. This means that when the angle is 120 degrees, the diagonal length is increasing at a rate of 10 centimeters for every radian the angle increases. This final example reinforces the process of setting up and solving related rates problems. Let's recap what we've learned today. We started by understanding that the derivative dx represents the instantaneous rate of change of y with respect to x. We saw how this concept applies to various real-world scenarios, from the rate of improvement in a child's ability to the marginal cost of production in a factory. We also explored related rates problems, where we use the chain rule to find the rate of change of one variable when it's indirectly related to another through a third variable. We worked through examples involving geometry and trigonometry. You are now equipped to use derivatives to model and solve problems involving rates of change, a key skill in IB Mathematics AAAHL. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then check your solutions. Here is your first practice question. The estimated future profits of a small business are given by P of t equals 2t squared minus 12t plus $118,000, where t is the time in years from now. Find the rate of change of profit after 8 years and explain what this value means. Pause the video now and attempt the question. Welcome back. Let's go through the solution. First, we find the rate of change of profit by differentiating P of t. P prime of t equals 4 minus 12. Next, we substitute t equals 8 into the derivative. P prime of 8 equals 4 times 8 minus 12, which is 20. The units are $1,000 per year. This means that after 8 years, the profit is increasing at a rate of $20,000 per year. The business is growing. Here is your second practice question. The cost for making X pairs of denim jeans per day is C of X equals 7,800 plus 6X plus 12X to the power of $0.7. Find the marginal cost function C prime of X and use it to estimate the cost of making the 221st pair of jeans. Pause the video now and attempt the question. Welcome back. Let's go through the solution. First, we find the marginal cost function by differentiating C of X. C prime of x equals 6 plus 8.4x to the power of negative 0.3. To estimate the cost of the 221st pair, we evaluate the marginal cost at x equals 220. C prime of 220 is approximately $7.49. So the estimated cost of making the 221st pair of jeans is approximately $7.49. Here is your third practice question. The total cost of running a train from Paris to Marseille is given by C of V equals 1/5 v squared plus 200,000 over v euros, where v is the average speed in kilometers per hour. Find the rate of change in the cost of running the train for an average speed of 30 kilometers per hour. Pause the video now and attempt the question. Welcome back. Let's go through the solution. First, we rewrite the cost function to make differentiation easier. C of v equals 1/5 v squared plus 200,000 v to the power of negative 1. Next, we find the rate of change of cost by differentiating C of v. C prime of v equals 2/5 v minus 200,000 v to the power of negative 2. Now we substitute v equals 30 into the derivative. C prime of 30 equals 2/5 times 30 minus 200,000 over 30 squared, which simplifies to 12 minus 222.22, giving us negative 210.2. The rate of change is approximately negative 210.22 euros per kilometer per hour. The negative sign indicates that at this speed, increasing the speed will decrease the cost. Here is your fourth practice question. The height of a shrub T years after it was planted is given by h of t equals 20 times the natural logarithm of the quantity 3t plus 2 plus 30 centimeters. T is greater than or equal to 0. Find the rate at which the shrub's height is changing 3 years after being planted. Pause the video now and attempt the question. Welcome back. Let's go through the solution. First, we find the rate of change of height by differentiating h of t. Using the chain rule, the derivative of ln u is u prime over u. So, h prime of t equals 20 times 3 over the quantity 3t plus 2, which simplifies to 60 over 3t plus 2. Next, we substitute t equals 3 into the derivative. H prime of 3 equals 60 over the quantity 3 times 3 plus 2, which is 60 over 11. The rate of change is 60 over 11 centimeters per year, which is approximately 5.45 centimeters per year. This means that after 3 years, the shrub is growing at a rate of about 545 centimeters per year. Here is your fifth and final practice question. The voltage in a circuit is given by V of t equals 340 sine of 100 pi t volts, where t is the time in seconds. At what rate is the voltage changing when t equals 0.01 seconds? Pause the video now and attempt the question. Welcome back. Let's go through the solution. First, we find the rate of change of voltage by differentiating V of t. Using the chain rule, the derivative of sine of u is u prime cosine of u. So, V prime of t equals 340 times 100 pi times the cosine of 100 pi t, which simplifies to 34,000 pi cosine of 100 pi t. Next, we substitute t equals 0.01 into the derivative. V prime of 0.01 equals 34,000 pi times the cosine of 100 pi times 0.01, which is 34,000 pi times the cosine of pi. Since the cosine of pi is negative 1, V prime of 0.01 equals negative 34,000 pi. The rate of change is negative 34,000 pi volts per second. The negative sign indicates that the voltage is decreasing at this instant. That concludes our exploration of rates of change. We've covered the fundamental concepts, worked through several examples, and practiced with IB-style questions. Remember, the key is to identify the variables involved, find a relationship between them, and then use differentiation to find the rate of change. Always pay attention to units and the physical interpretation of your results. Thank you for watching. Keep practicing, and you'll master this important topic.